So you want to talk about uncertainty in which terms?
The plus and minus when you have a measurement. So we need to...
Yes, of course. So uncertainty defined as the plus minus when you have a measurement, which is a kind of nice definition. Probably somebody will recycle it. When I ask in an exam, what is the uncertainty? Somebody will say, the plus minus after the measurement. Okay. Let's try to be a little bit more scientific. Well, actually, I wouldn't say really scientific, because it's pretty much a definition. I would define it as lawyer definition. Because the whole scientific part ends where we say, okay, we measure something, but we cannot say which is the real measurement of that physical quantity, okay? So because of several reasons, because anytime you measure something, you interfere with the circuit of measurement. So somehow you take some energy out, and the circuit is not the same it used to be before. Or even just because your instrument doesn't have infinite digits. So you have 7 digits, voltmeter with 7 digits, fine. Still you will be able to tell something about, at most, the 7th digit. But you cannot go to the 24th digit. You cannot go there. So, and you cannot say it's 0. Simply it's a quantity that you don't know. So, plus many other things. Generally speaking, we don't know, we cannot say the exact value of a measurement, of a physical quantity that we measure, okay? So that's the problem when they say, okay, the error is the difference between the true measurement and what we get and what we measure. The true, value and the measured value makes no sense, because you don't know the true value. You will never know it. So if you don't know the true value, you cannot know even the error. And even if you knew it, just, it doesn't make sense to give a measured value and then the error. Just give me the true value. So rather than the error, we talk about uncertainty, where we have, I don't know, if you measure a voltage, you have a measured voltage, and then you have a range of value. The definition says a range of value that you can reasonably associate with the measurement, which is a lawyer definition, because what does it mean? What reasonable means? So as a matter of fact, if you really want to express the uncertainty, you always need to specify what you did, okay? So you always need to say, okay, I calculated this way, assuming this, and then the person who receives the calculation will assess and say, okay, these assumptions are reasonable. I consider this value of calculated uncertainty as reliable or not, okay? So, anytime you give the uncertainty, there is not, in my opinion, okay, that's what I believe, that there is not a value of the uncertainty. Because there are so many assumptions that you have to make that it's an estimation of the uncertainty. And according to different assumptions, if you take different assumptions, then you can get different values. So always specify what you're doing. So there are 2 main values, do you remember, of the uncertainty?
There's the uncertainty and the error.
No, the error is, okay. Well, yes, there is the error. We talk about error only when we can define it. We can so not define it, when we can calculate it, okay? For instance, let's say that you want to measure a resistance, okay? So DC value of the resistance. Here you have your meter. Here your resistance that you want to measure. You put a voltmeter, you put the ammeter. Let's say here you have a current of 1 milliamp. Okay? So you measure this current with the ammeter, you measure the voltage with the voltmeter. So here you measure the current, here you measure the voltage, and you know that the resistance will be the measured voltage divided by the measured current, okay? This is not really true because you know that the voltmeter has some internal impedance, okay? So you can consider the same circuit where instead of an ammeter you have a resistance, the resistance of the meter, which is typically low but it's there. Okay? Then you have a resistance of the voltmeter and then the resistance that you want to measure. Okay? Mm-hmm. What you measure is the voltage between this point and this point, which is Vm, and that's fine. But the current is not the current in the resistance that you want to measure. Is the current, let's say, X plus the current in the voltmeter, okay? So if you want the current in the resistance X, you have to consider here, in this equation, Ix, okay? And you know that, we used small case, and you know that Ix will be the current Im, okay, minus the current in the voltmeter. So you have to take the current that you measure, and you have to subtract the current in the voltmeter, which will be low, fine, because the resistance of the voltmeter is very large. Well, but it depends. If this resistance is also large, if it's comparable, then good luck. Okay. So this is something, the error introduced in your measurement by the voltmeter is something that you can estimate. Okay. Why? Because typically you know the value of the input impedance of the voltmeter. If you don't know it, you can calculate it. Okay. Then, but typically it's a parameter, like you don't really need to calculate it. You have a parameter in the datasheet of the voltmeter. You know the voltage here. Oh,
no.
Terrible. So you know the voltage because you measure it. So the voltmeter is measuring the voltage on its own terminal. So you know that the current in the voltmeter will be the voltage read by the voltmeter divided by the resistance of the voltmeter. And then you can correct this value here. Which means that in this case we can have an estimation of the difference between the actual value of R and the value of R that we obtain if we use Im here. Okay? This is the wrong value of R, let's say wrong in quote marks. And we can obtain the correct, again, quote marks, value if we use Ix instead of Im, the current that we measure. So we make a correction of an error, and in this case, an error introduced by the method of measurement, it's something that we can estimate. We take the value of the voltage of the measured voltage, we divide it by the resistance of the voltmeter, and we get the correction, how much we have to correct the reading of the current. We can estimate it. We can say is some particular value, and therefore we call it error, because we can say it's that value. We can calculate it. It will not be perfect, because still we don't know perfectly the value of this resistance, but at least we have an estimation precise. So this is something that we can correct, and if we can calculate it precisely, more or less, and subtract it from your reading, then it's called error, okay? So yes, this is the error introduced by the method, and we can call it error. But then there is another thing, which is uncertainty, which is another thing. In that case, you cannot say, I have to subtract, I don't know, I measure 1 milliamp here, so I measure 1 milliamp, and I don't know, the current in the voltmeter will be 0.001 milliamp, okay? I cannot say it will be 0, I don't know, let's give it a more funny number, 87, okay? So, I cannot say it's 0.0087. I have to give a range and say, okay, more or less I expect the value to be within this, of the measurement within this range, okay? And this is the uncertainty, because as the name itself suggests, you are uncertain of the value, okay? And there are two types of uncertainty. Does the word type trigger anything?
Yeah, there's A type and B type.
Okay. And do you remember what are they related to? So what is A type and B type? Whatever, one of them.
One is from the instrument you are using.
And the other?
Is from the equation that you are using to measure.
One is, their definition says, from statistical observation of data, which means that you don't change anything. You have always the same circuit of measurement, but the instrument is giving different values. For God knows reason what's going on there, okay? So if you have there, let's say, that you are observing in time your resistance, you want to measure your resistance, and you get some fluctuation of data, okay? So what do you do is to take the average. So you take the average of the data, and then you consider two types of situation. For instance, if you have a resistance, again, Rx, and this is again the average. So let's consider two experiments where we have, in time, we observe the resistance, we measure this resistance, and they have the same average value, but in this case, the scatter of the value is way larger, okay?
Okay.
So here, I don't know, you measure 101.3 ohms. In both cases, the average is always 101.3 ohms, okay? But here, all the points that you observe, all the measurement, are close to the 101.3 ohms average. Here, they are far away, okay? Clearly, you have the feeling that this is less precise, but probably precise or accurate. I don't know, because then there is a difference between what is accuracy, precision, but let's forget. This is a better measurement than this one, okay?
Really?
Eh? So this is the best.
Okay.
This is the worst. This is a worse measurement than this one, okay? So we have to quantify it, okay? So how do we do it? How do we quantify the scatter of the resistance around its average value?
Some distribution property.
What do you mean? Well,
I remember it involves the square root of 3.
hmm?
It involves the, no?
No. Let's take this. What is
Okay.
this? Let's see. This is each sample is Ri.
The deviation.
Standard deviation. So you
Yes,
take
yes.
the difference of this each point to the average. Okay. This difference Ri minus Rx average. So
Divided
for
by.
each point, you take the difference. Now, if you sum them all, you get 0. Okay? Because as a definition, the average is that value which is right in the middle, so that if you sum all the plus and minus scatter, you get 0. So you have to square them, because you don't care if they are positive or negative. What you care is they are far from the average. Then if they are far from the average on the top, or far on the edge or on the top, you don't care. They are far from the average. Fine. So then you have to square them to get rid about the sign, and then you get the average of the scatter. So what you do is to calculate how large in average is the scatter of, is the difference between the single point and the average value, okay? So you want to know how large is this scatter, how large is this difference between the single point and the average for the points that you measure, okay?
For the whole graph.
For the whole graph, so you take 10, 20, 100, 1,000, and that's the standard deviation, okay? Okay?
Okay.
So standard deviation means that what's the typical deviation of the single point from...
What's the average distance between the average and a
exact.
point?
What's the exact?
Yeah.
The average distance between the point and the average, okay?
We should have a sum before that.
Yeah, of course, then you have to sum them all.
Yes.
Okay.
And then we should divide it
by the number or n-1, depends on, and then you have to take under because eventually if you
it's RMS basically.
RMS is something different, because RMS you square RMS, for instance, if you have a voltage, is square of the voltage. Okay, you square the voltage. Then you integrate it in a period, okay? If you have a periodic signal, generally speaking, it doesn't need to be a periodic signal, but if you handle periodic signals, period. So, and then you take something like that. The formula looks similar, but keep in mind that in RMS value, you have also the DC value, okay? Here I take this part, okay? So only the part which deviates from
the mean.
From the mean, okay? Because what I want to understand is how far each thing, or which is the typical distance between the points and the mean. So that is the standard deviation. Now the reason I square root is that if I square here, I have ohm squared, okay? So here I sum ohm square, ohm square, ohm square. At the end of the day, I want some value in ohms. So I have to make the square root in order to have back ohms, okay? And that's it. You don't know what is causing this scatter, but if the device is there, it's always the same, nothing touching anything, well, there could be some other phenomena that you don't see that is introducing some error, but whatever. You expect to see always the same value, but you don't. You see that it changes in time, and if you see that it changes in time, you have to say, okay, fine, I take the average, or I take the standard deviation. The standard deviation becomes my uncertainty of type A, okay? So this is the uncertainty type A, okay?
Okay.
So this is simply the standard deviation. for instance, I don't know, there is some interference, some electromagnetic field inducing something in your circuit. It's random. It does, or not even random, but maybe it's deterministic, but it's changing, it's introduced by some other colleague in another laboratory creating huge magnetic field disturbance. It does affect your circuit. Theoretically, the resistance is always the same, okay? Or practically, the resistance is always the same, but you read something else because there is some interference, or maybe it's even conducted on the line, whatever, okay? And therefore, the device under test is always the same, but the result changes in time because there is some interference from other sources, okay? Fine. This is type A. And what about type B?
Type B is from the measurement itself.
Oh, it's very simple. The definition says everything else. Because they were so kind. Of course, the adjective I was trying to look for was not kind, but I think I cannot say what I think. And they say, okay, type A is because of the variation that you see in time, okay? And type B, it's simple, is everything else, okay? Everything else is type B. Thank you very much for the water.
Pleasure.
So, let's see some examples of sources of uncertainty. Well, first of all, the instruments themselves, thank you. The instrument themselves, okay, so whatever, you have, I don't know, voltage source, you have one resistor, another resistor, voltmeter, and you want to measure this voltage in this circuit, okay? You take your voltmeter, it gives you some number, I don't know, 1.3789 volts, okay? And you don't know this value perfectly, okay? You don't know it because the voltmeter is not a perfect instrument. So, if you go in the datasheet of the voltmeter, when they sell you the voltmeter, of course, they make some calibration, if it's a good voltmeter. If it's something that you buy for $5, shipping included on eBay, definitely they don't make any calibration whatsoever. But if it's a good quality voltmeter, they need to make some calibration, and they tell you how long it lasts, okay? Because all the voltage reference whatsoever you have inside has some drift in time.
Yeah.
So they can tell you that with those components, they know, they characterize those components, they know how stable they are in time, with temperature and so ever.
Wow, it's like a whole nother science.
They know that they keep stable within a certain range for some time.
And temperature.
And temperature. So typically they tell you the accuracy is given, I don't know, for some voltmeters they tell you, okay, the accuracy will be some percentage of the reading. Okay, let me erase it because I don't have space anymore. So they tell you that the accuracy will be some percentage of the reading, so Vm is the voltage that you measure, plus another percentage of the range, okay? Why? Because there are some sources of uncertainty which depend on the range, and like because of the circuit that you have inside, you have some fixed contribution, which depends on the amplification gain of the amplifiers that you have for signal conditioning inside. And that doesn't change on the quantity that you measure. And then there is some contribution given by which depends on the value that you measure, okay? So,
because when you're in a certain range, it's a different resistor, and that resistor will have a different uncertainty.
You have, like, I don't know if you studied, if you remember what we did with the operation amplifier. For instance, there is offset, the offset voltage of the operation amplifier. That's some value, which is
multiplied
times the gain, roughly, and it's a constant value which doesn't depend on what you measure, okay? So in that case, it's better, of course, to have a voltage which fills as much as possible the range, okay? Because that contribution is constant, and so it's much better to have a voltage which is not small compared to the range, but is bigger, because then the constant value doesn't weight that much, okay?
Yes.
That is the accuracy class, the accuracy range. In other case, the accuracy is given by a percentage of the range, okay? They tell you the accuracy class is 1%. They tell you that it's 1% of the range, okay? Then that's the problem, because then they tell you, okay, fine. You theoretically would need a distribution of probability of the measurement in that range of accuracy, okay? So if this is the accuracy, and you know that you have this distribution of probability, you say, okay, I can say that,
just to be clear,
I don't know.
That's Gaussian distribution, right?
That could be Gaussian or something deformed with respect of Gaussian, whatever. Let's say that here we are low enough that we can say it's 0, okay? So we can say that it's inside this range. And then you can say, okay, if I take one standard deviation, I will have some coverage of the probability. Or if I take 2 sigmas and so on, you can take whatever you want. The problem is that typically we don't know which is the actual distribution. And manufacturers don't really disclose anything like that. So either you make some calibration, so you take some precise source of voltage, you can change it and you can see how it distributes, okay? But that would be insane. In typical everyday life, you don't do it. Like, otherwise you would be a metrological institute and not somebody who uses a voltmeter. Otherwise, say, okay, you know what? Uniform distribution, and give. So I say that in this accuracy range, I say, okay, fine. I have here, this is my accuracy range. And I say, okay, it's constant, okay? And fine. But in this case, the sigma is one sigma is very simple to calculate, because if you have a distribution which is uniform, what does it mean? It means that you have the same probability to have the value in any point of this range, okay? So there is no higher probability to have the measurement here in the center. It's the same, okay? Which is like an easy solution when you don't know anything. When you don't know anything, you say, oh, okay, I'm just take uniform. Fine. So in that case, you take the uncertainty. So one sigma, one standard deviation of uniform distribution, it will be the accuracy divided by square root of 3, okay?
There it is.
So, here it depends on the instrument. When you put some instrument inside your circuit to measure something, what you have to do is to take the the manual of the instrument, check the accuracy specification of the instrument, which is one parameter. If the instrument is good, that they have to give you, okay? So you expect them to make some calibration before selling you the instrument, and theoretically you are supposed to calibrate it periodically. You calculate the accuracy. Then, if you have some information about the statistical distribution, you take 1 sigma given by the statistical distribution, or if you don't know anything, you take the uniform distribution, and you know how to calculate 1 sigma, 1 standard deviation, by taking the accuracy range and divided by the square root of 3, by square root of 3. Again, we take the standard deviation, okay? We use this principle with type A uncertainty.
And type B.
And so, because we want to know how large is the spread, okay, of values. We calculated the standard deviation with type A and also with type B, the same. In this case, if you have a uniform distribution, standard deviation is the range divided by square root of 3, okay? Fine. Then, there are other sources of uncertainty, and they pretty much depend on whatever you are doing, okay? So, anything which introduces some uncertainty must be considered. For instance, typical example of a measurement. You want to measure a current, okay? How would you measure in the simplest way a current?
No, Ohm's law.
Ohm's law, so let's say that we have a circuit, whatever is the circuit. Here we have some source of voltage, and we know that we want to measure the current here, okay? So what we do, we put a small resistance,
Yes.
and we measure the voltage, okay? So we measure the voltage, and you know that the current will be, let's call it IM, because we measure it, the voltage reading of the voltmeter divided by the resistance of this ammeter. Okay, so this becomes our ammeter. As you see here, we have some resistance. It might be small, but there is a resistance which interferes with the circuit. So if you don't have this ammeter which measures the current itself will be larger, okay? Because you have less resistance in the circuit. Okay, so we take the voltmeter. We know the uncertainty of the voltmeter because we take the accuracy of the voltmeter. We assume uniform distributions divided by square root of 3. We get the standard deviation. Fine. What about the resistance?
Well, the resistance has some what's it called? Tolerance.
Tolerance, okay.
Yes.
So you can go to the shop and say, give me 5% tolerance resistance, 1%, or if you're very rich, instead of going to any shop of electrical components, you go to some to order some very nice standard that can have 0.0 blah 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 percent tolerance, very very precise, where you know very very well. Okay. So it means that if you put here 1 ohm, you're not sure that this is 1 ohm.
Yeah, it has a deviation.
Maybe it's 0.9997. So maybe the resistance is not 1 ohm, but it's 0.9997 ohms, okay? Which means that if you consider here 1 ohm, well, that's not the correct value of the current that you're going to calculate, okay? But again, you don't know this value, okay? You don't know it. You assume it's 1 ohm. You can measure it. You can measure it, you can calibrate it, but again, even if you calibrate it, you have some uncertainty in the calibration, okay? So definitely you will always have some uncertainty on the resistance. Typically, again, if you assume the uniform distribution, you know that it will be 1 ohm plus minus some delta R, okay? You have, again, your accuracy, 1%, 2%, 0.001%. You take, again, your accuracy, you divide it by square root of 3, because you assume uniform distribution, and you get one standard deviation of the distribution of the resistance. Okay?
And the accuracy is that tolerance that they've been given?
Yeah, so 1%, 2%.
So you would put there 0 points.
For instance, if you have 1 ohm, it's very simple because you 1 on 1%, 1 divided by square root of 3, blah, blah, blah. Okay? Fine. Again, like in this case, probably you might have some statistical distribution, because if the manufacturer sells you one resistance out of the batch, and before selling you the resistance, they had made some testing, and in the datasheet they give you some distribution of the test. In this case, I really don't believe it will ever be uniform, the distribution.
Because they can use that distribution to divide the components up, and then they can know that.
Exactly. Then at some point they will reject some bad ones and so on.
Yeah, and then they can put the other ones in a higher class.
But yes, but not always they test every single component. It depends on what you are buying. Okay, but typically they take a production line, they test 1,000 of them, 2,000, whatever. And they say, I assume that if I don't change anything in my production line, I will produce now 1 million, 2 million, 10 million resistors, and I assume they will have always the same distribution. So I think I will make a test on 1,000 of them, and then I assume it will be the same for all of them. And then they sell it to you in a blind way. So they have not been tested. Only a statistically significant sample of them have been testing, they give you some distribution, and again, you try. Again, you have to always make some assumption. In this case, you assume that the statistical distribution of those resistances is equal to that of what have been of the batch that was tested. You have to declare it. Otherwise, you take that single resistor that you're using, you calibrate it, so you measure it. You take the then you measure you calculate the uncertainty of your calibration, and then you use specifically that value. Okay. Fine. Okay. So you have larger, smaller voltage, larger, smaller resistance. You have for the same current, larger, smaller voltage, and therefore you get a different value. Okay. So now we have another source of uncertainty. So we have the uncertainty of the voltage itself. And then you say, okay, fine, let's assume that the voltage is measured perfectly, but still there is some uncertainty, because you don't know exactly the value of the resistance.
Okay.
So you have two sources of uncertainty, the uncertainty of the voltage and the uncertainty of the resistance. How do we combine them to get the uncertainty of the current?
You get a partial derivative of that equation with each variable, and then you multiply it to the uncertainties of those variables.
Okay. That is the formula. What is the meaning behind that?
So when you take a derivative, you're essentially getting a slope of something, right? So when you take the partial derivative of each component, so you take the partial derivative of the equation with respect to the resistance, you're getting a slope of something in the resistance. And the same thing for the voltage, you're getting a slope of something in the voltage. And that slope represents the uncertainty in that part of the measurement.
It doesn't represent exactly the uncertainty, it represents how it propagates.
Okay, how the uncertainty, adds up into the equation, but it doesn't add because...
So the voltage equal resistance times current, correct? Something like that.
Yeah. Well, wait. Shouldn't that be R at the bottom there? And less...
This is the characteristic of resistance, okay?
Okay, yeah.
Generally speaking.
Okay.
Now, let's say that we have okay, the purpose here was to measure the current, okay? So, for instance, if I have a current here, we have to flip this characteristic, okay? More voltage, more current, okay? So what does it mean here? It means that we have a measured voltage here and some uncertainty, okay, of the voltage. Correct?
Yes.
So when we measure the voltage, we say, fine, I don't know what is the exact value of the voltage. I know that there is some range I can associate reasonably with the measurement of the measurement that I want to do. Okay, so measurement is what you want to measure, and this range is given by the uncertainty of the voltage. I make my assumptions, I calculate the uncertainty, and say, okay, I can reasonably expect to see the voltage in this range. Okay. What does it mean? If this is the transfer function between the result, the current, here I use the current, and the voltage, okay? If I have a larger voltage, I have a larger current, okay? Sorry. So this is the current. So if instead of the real, and again, it's not correct, real, but
actual,
not even. Let's say that, because I don't like to say real because the central point is not necessarily the real, okay? So you have
the virtual real point.
So here you have Vm plus uncertainty of Vm.
And then you have minus.
And this is Vm minus the uncertainty of Vm, okay? And this is Vm. It is natural for a lot of people to say that this is the real value, but that's not true. Maybe the real value is here. Maybe the real value is here. Maybe it's here. Maybe it's here. Okay? So, let's say, is it clear? So when you give
it's not clear why it would be outside that range.
Well, why not? I take only one sigma, okay? One sigma means that I take one standard deviation, but doesn't mean that it should be within one standard deviation. Okay, it could be 2, 3 standard deviation, even 10 standard deviation. You never know. Just consider the example we did at the beginning with type A uncertainty.
Okay, yeah, it could be one with the maximum deviation from the average.
So here we have our standard deviation, and then one point here, and maybe it's here.
Okay, it's that one measurement that's an anomaly.
Or not necessarily that value, but maybe something more, something less. It doesn't necessarily mean that it should be in that range. So when we say reasonably, means that, okay, with some degree of confidence, okay? But we don't know exactly what it is. So rather than using this VM, which is somehow misleading, in my humble opinion, I would draw directly a range, okay? So here's the current. No, here's the current. Here's the voltage. So what we say is that there is Vm plus uncertainty of the voltage, Vm minus uncertainty of the voltage, and that is reflected, is translated into a range of values here where I have Im plus the uncertainty of the current and Im minus the uncertainty of the current, okay? Correct? So if this slope is different, let's say that I still have the same range of Vm plus uv and Vm minus uv, okay? But the slope is different. In this case, I minus ui and I plus ui, this range is smaller, okay? If it's larger,
Yeah, then the range will be greater.
Range are great, okay? So what you need to do is to calculate this slope, because this slope tells you how the very same range of uncertainty of the voltage is translated into the range, the final uncertainty of the current, okay? So that's why you take the function here is current, which is the final, the output of the equation, okay? Because you want to measure the current at the end of the day. And as a function of the voltage, okay, which is the input, let's call it output, okay? So the voltage here is the input. The output is the current, so you measure V and you want to recalculate the current. And in this case, the current is clearly, the function is the voltage divided by R, okay? And then how do you calculate the slope? Okay? You have to calculate the slope of I with respect of V, okay?
Yeah.
Which is 1 over R.
Yeah.
Okay. This tells you which is the slope by calculating it as the derivative of I with respect of R, okay?
Yes. Yeah, because,
and
yeah. Nothing.
Go ahead.
Just explaining a derivative to myself.
The derivative tells you which is the slope of the function. Okay?
Yeah, but now this is a partial derivative, so this is the slope.
The partial derivative just because here you have different variables.
Well, actually, yeah, okay, sorry to make it more complicated, but it's the partial derivative of the voltage, but the resistance is constant, so you could actually make that just a normal derivative because V is
first of all, it's partial derivative of the current, not of the voltage, with respect of the voltage.
Yeah. So what's the slope of the
yes, when you make the derivative, okay, if you make this now we are considering the uncertainty of the voltage, okay?
But the resistance also has
then exactly. Then we will make the opposite, okay?
Yeah.
So
so we get the slope of the voltage.
The slope, and then we say, okay, the slope we multiply times the uncertainty of the voltage to understand how large will be the uncertainty of the current. So what we do is to, like for instance, if you have a small value of slope, you have the same range and you get out a small uncertainty of the current. If you have a large slope, okay, you get clearly a larger range of uncertainty. Okay? Fine. And you can even see it because it's 1 over R, right? Okay, the derivative of the current with respect of the voltage is 1 over R. What does it mean?
Because it's V to the power of 1, 1 minus 1 is 0, anything to the power of 0 is 1, and then...
What are you talking about?
How you get the derivative of V over R.
I'm missing you.
Just how you solve it.
Not missing you. I don't understand what you're saying.
Because when we it's basically how we got 1 over R. That's what I was
saying.
Okay. Yeah.
So this is the derivative. Okay?
Yes.
Okay.
Yes.
Fine. So let's say that you have a large resistance. Okay? Large resistance means that for the same value of voltage, okay, you measure the same value of voltage, but large resistance you have. Let's say that you have 1 volt, okay?
Yes.
1 volt. And you have 0.1 ohm. Let's make some example. Okay, what is the current?
Be 1 milliamp.
Formula. You have V divided by R, okay? The voltage is 1 volt. The resistance is 0.1 ohm. It will be what?
So, what?
Hmm?
I'm sorry, I can't figure it out at the moment.
Okay. The voltage is equal to resistance and the current.
Yeah,
It's
I
correct,
got you,
okay?
I got you. 1
So,
divided by...
1 divided by 0.1 is?
Sure, I'm blank, so sorry.
10 amperes.
Oh, yes, it multiplies it, yes.
Okay? Not such a difficult, okay? So if you have 0.1 ohm, you have 10 ampere. If I have the same voltage, 1 volt, and I have 100 ohms, okay?
Then it would be 1 milliamp.
Then I have the current will be voltage divided by the resistance. 1 volt divided 100 ohms is 10
Oh, 10.
milliamps, okay?
Yeah, it's not 1,000. Yeah.
Okay. So for the same voltage, say I have 1 volt here. If I have a large resistance, it means that I have a small current, okay? If I have a small, so this is corresponding to large R. Okay. If I have a small resistance, it corresponds to
A large current.
this is small resistance. I have a large current, okay? But look carefully about the uncertainty. Now I will erase this so that I will make a better graph. Let's repeat again the graph, okay? So this is the voltage, and this is our uncertainty of the voltage. Look at here, okay? So this is voltage and the current. Okay, so this is large R, and this corresponds to small r. Correct? Because small r means that you have a larger voltage.
Larger current.
Larger current, correct. Now, if I have larger r, I have a small range
Of uncertainty.
of uncertainty. Okay? If I have a small r,
A larger range of uncertainty.
large uncertainty of the current, correct? So, if for the same value of uncertainty of voltage, I have a large R, I have a small uncertainty of current. If I have a small r, I have a large uncertainty of the current. So it's vice versa. It's in opposite proportion. And that's exactly
What you see there.
what you see. It's 1 over r.
Wow, okay.
Does it make sense?
Yeah.
Okay. But I think visually you see it better if you see here, because you can see really the characteristic, and you say, okay, if I want to translate, if this is the characteristic which translate each point from voltage to current, well, you take each point of this characteristic, you translate into current, and then this range corresponds to this range of current, okay? What?
Isn't it area? That area corresponds to that area.
It's not an area. It's a range of voltage.
No, it's like this. This area here is equal to this area.
No.
Because when this is greater, you have a greater area and a greater area.
Look.
It makes, like, I understand, like, what's happening, but just the words.
Look. This characteristic means that if you have an input voltage, you get an output current.
Yeah.
That's it.
Yeah.
Point. So if you have this point to this point of minimum and maximum value of voltages, you get to minimum
and
maximum.
Yes.
Point. This characteristic could be of a different shape, okay? Like, again, let's watch this characteristic. Let's draw it better. I is equal to V divided by R. Let's now plot I versus the resistance, okay? How does it look like?
Okay, give me a second. Sorry, I'm just exhausted.
It's something over R. Good. Okay. Okay.
Sorry.
So it's something like that, okay?
I wanted to make it linear, but I was like, no, it's not.
Why not? It's not linear, okay? And again, you do the same thing here. You say that this is R, that you measure or calibrate or whatever is the value, the nominal value, okay, of the resistor, 1 ohm. Then you have the tolerance, fine, you calculate the uncertainty. This is Rm plus the uncertainty of the resistance, and here minus the uncertainty. Then,
oh, okay, I see.
Now, theoretically, you should do something like that, okay? So you should translate the maximum and the minimum point and get, again, I plus uncertainty of I and I minus uncertainty of I. But what you typically do, again, is to take the derivative in this point, okay? So you take the point there in the middle. Now, I will make another drawing because otherwise I don't have space to make a nice graph. Okay, so what you do is not to consider these points on the actual characteristic, but you take Rm and you calculate the derivative of the current with the respect of R. But this derivative is now a function of R itself, okay? Can you calculate it from here? Just tell it. What's the derivative of I with respect of R?
It's going to be minus 1 V over R squared.
Okay. So now it depends on R, which is obvious because, again, the derivative is the slope. So here the slope will be this steep. Here the slope will be not very steep, okay? Correct? So now we want the slope in this point where we are measuring the current and according to the value of the resistance. So we take the slope in this point, and then we linearize basically this function. We say instead of taking the real function, we take the linearization of the function in this point, and again we multiply the derivative of the current with the respect of the resistance times the uncertainty of the resistance to get the uncertainty of the current, okay?
Wouldn't it be the uncertainty of the current? So it's this.
That's the same. If you have here this plus UR, you get UI, or twice UR, you get twice UI.
Well, no, because of this area here. You're not.
You're not talking.
We're talking.
There's
about
no
this.
area. There's no area.
Okay, range.
There's a range here. From here, you go to here, and you go to here.
Yes.
From here, you go to here, and you go to here. Okay? Here, the only difference is that here you have maximum, which corresponds to minimum. So the maximum resistance corresponds to the minimum, and the minimum resistance corresponds to the maximum, okay? Which is obvious because if you have a larger resistance, you have a smaller current and vice versa, okay? So instead of taking the actual point of the function, which are this point, which would give this value and this value, we take these points on the linearization, okay? Is that clear?
Yeah.
Are you sure? Okay. So, what you do in your basically in your circuit is to consider all the possible sources of uncertainty. So let's say that you are measuring a current, and it depends on voltage, resistance, blah, 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 okay? So we can say that X out is what we measure at the end, okay? The final quantity that we want to measure, in this case is current. It depends on, or let's call it Y.
Yeah,
okay.
X out. What?
Why is so wet?
That's what she said.
Oh. So Y is a function. Are you? So Y is a function of different variables. So it's a function of x1, x2, x3, and so on. Okay, there could be several different values in the circuit with which give a contribution to the uncertainty. Okay. In this case, in that circuit, very simple. We have Y was the current, because at the end we want to measure the current, and it was affected by the voltage and the resistance, okay? Then, if you want the uncertainty of Y, of the final value, or the final physical quantity that you want to measure, will be what? You have to take the derivative of each and every variable giving a contribution to the uncertainty, so the derivative of Y with the respect of each of these variables, okay? Then you have to multiply times the uncertainty
of that variable
with the respect of that variable. Then you cannot then sum them up all together. You have to sum them quadratically, okay? You have to sum them quadratically.
and divide them by the number of components.
No.
Or just root them?
No need. Why?
Because I'm seeing it as some sort of average.
No, it's not.
No, there must be a square root there.
There must be a square root for sure, because we have summed them quadratically, okay?
Okay, that makes more sense.
So, for instance, if I have the uncertainty of the current, okay?
Oh, and these units still stay the same because...
Exactly.
Yeah.
So if you have the uncertainty of the current here, remember, the current is the voltage divided by the resistance. And the derivative of the current with respect of the voltage is 1 over R, okay? So in that case, we have two sources of uncertainty, the voltage and the current. So what we have to do, we have to take the uncertainty of the voltage and multiply it times the derivative of the current with respect of the voltage, correct? And the derivative of the current with respect of voltage is 1 over R.
Mm-hmm.
So 1 over R. Then we square it. Then we have the uncertainty of the resistance. So we have to take the derivative of the current with respect of the resistance, which is minus negative V divided by R squared times the uncertainty of the resistance, again squared, and everything under square root. Why? Because if you watch here, we have what? Voltage.
That's V over ohms.
This is voltage divided by ohms. Okay.
And then this is voltage times ohms over ohms squared, which is V over ohms.
So here you have voltage divided by ohms square. The uncertainty of the resistance is ohm. Okay. So this goes away, and you get again ampere. Okay. But that means that you have ampere squared plus ampere squared. Okay.
Rooted.
So it will be,
cancels.
I can write it here, ampere squared plus ampere squared, okay? And this gives you at the end of the day
Amps.
amps, okay? So it makes sense.
Mathematically, yeah.
Mathematically, yes, maybe there is some mistake, but...
No, that's right.
No, I mean, that could be, if this matches, doesn't mean that this is correct, okay? If it doesn't match,
Then
if you have
definitely something
ohms
wrong.
plus volts, you cannot sum orange and potatoes. If you have volts square plus ohm square, then definitely something is wrong. Okay?
Yeah.
But if it's correct, doesn't mean that it's correct. There could be some other error, which still gives the correct unit of measurement.
Yes.
Okay? Why we do something like that, and which is the assumption behind that? The assumption is that these two sources of uncertainty are not correlated, okay? What does it mean? It means that there is no correlation between the uncertainty of the voltage and the uncertainty of the resistance. In other words, if you plot the, again, this is, from the statistical point of view, it's not very correct, but I will try to say it in a way that it can be understood, even if not precise enough. This is the uncertainty of, no, this is the value of the voltage, the resistance, and we have some uncertainty, okay? Uncertainty of, so this is Vm, and this is Vm plus uncertainty of the voltage, and here is Vm minus the uncertainty of the voltage. And here we have the resistance plus the uncertainty of the resistance, and this is the resistance minus the uncertainty of the resistance, okay? If they're not correlated, it means that all the possible points are scattered like without any correlation, okay? They are randomly distributed in a circle which takes this edge by the value of the uncertainty. In that case, it turns out that you have to sum them quadratically. If there was some correlation, like if the graph was not scattered like that, but it was something like that. Like there is more correlation on one line, then you cannot do this sum quadratically. You do the sum, the quadratical sum, if they are distributed without any correlation one another, okay? Then you can demonstrate that the expected value of the uncertainty of the current will be given by a contribution which is weighted by taking the quadratical sum of the two things. Is this condition met? Well, yes. Typically, yes. There is no reason why, if the voltmeter is giving me a value of the voltage which is larger than the real one, then also the resistance should be larger. There is no physical link between, I mean, if you go to a shop and you buy resistance and this is larger than what you expect, because the shop assistant gave you a resistance which is not 1 ohm, but 1.005 ohms, and you, out of a batch you get a resistance which is slightly larger, it doesn't make more likely, more probable that the voltage will give you a larger voltage. There are two physical components separate, so they don't watch each other. The voltmeter doesn't watch the resistance and say, the resistance is larger, so I will give a larger voltage. No. Yeah. So there is no link, physical link between them. But if there is, then you should take it into account, okay? So this... that's what the partial derivatives do. No. Partial derivatives, it's independent. Partial derivatives tell you only as you how you translate an uncertainty on one source of uncertainty, the resistance, into the final. Yeah. But they're all dependent on each other because they're in the same circuit. Yeah, but you consider them one at a time. Yeah. When you do the partial derivative, you say, okay, now I consider the source of uncertainty given by the resistor, by the fact that I don't know which is the real value of the resistor. In that case, I consider the voltage is perfect. Okay? The voltage doesn't change. I calculated the partial derivative with the respect of the resistance because I say the voltage there doesn't change. It's perfect, it's constant. And that's why, if it's constant, you can calculate the partial derivative with respect only of that variable, okay? So you consider in this formula the voltage constant, and you calculate, and the variable which changes is R, and you calculated the variable, the partial derivative with respect of R, okay? Yes. So one per time, okay? So you take the partial derivative of I with respect of R, and you calculate the uncertainty of R. Squared. Then the partial derivative of I with respect of V times the uncertainty of V. And then, if these two sources of uncertainty are not correlated, are independent, then you sum them quadratically, okay? Only under that assumption, as long as it is, again, plausible, okay? And then you, of course, not only two, like typical mistake. People think that if you have 3, 4 sources of uncertainty, maybe there's some other component in the circuit which gives some uncertainty. They have to sum them with the square, with the cube. No. It's always them quadratic. They are always summed quadratic. Yeah, because the square root won't work then. No, but then they make the cubic root of the cube. No, it doesn't work like that. You have to always to sum them quadratically, even if you have 1,000 of different variables, okay? Wonder how... Is that surprising you? No, I'm just trying to imagine what the difference would look like if you square them and then root them, and then if you cube them and cube root them. Because... Huh? Yeah, you would expect it's the same, but it's not. It's not the same. I wouldn't expect to be the same. I sort of, like, obviously, it's just because... You know why I see it like that? It's like if you take x squared and you root it, you get x. And if you have x cubed and you cube root it, but then you sum, man. Yeah, the summing is what? Yeah, you're summing the cubed values and not the squared values. And that
like multiplies the sum. Yeah.
Okay, this is pretty much everything about uncertainty.
Okay, so show us how we join A and B together.
Then the same. Again, you don't have reason to expect uncertainty of type A to be correlated to the uncertainty of type B. Okay? So what you do, again, is to take the total uncertainty, which will be the square root of the uncertainty of type A square plus the uncertainty of type
B squared.
B squared, okay. Again, then it depends really on the kind of situations you have. So if it's something where there could be some correlation, whatever, always refer to the physical problem that you have to consider, okay? And again, give some explanation of what you are doing. So if you say, okay, the uncertainty of these several variables is not correlated, they are not correlated to each other, okay? Show it, explain why. Sometimes it's obvious, okay? Sometimes it's not. So show, explain why you assume these sources of uncertainty are not correlated to each other, and then you can say, I sum them quadratically. Okay? So always, whatever you're doing, explain why, because then somebody could say, okay, fine, I don't really agree with this assumption. So in my opinion, your calculations are not precise enough, or they are not reliable, I don't like them. And he can recalculate according to his own assumptions, okay? And again, sometimes, for instance, you hear about extended uncertainty, okay? So there is some uncertainty extended, which is a coverage, I think they call it coverage factor. So K times the uncertainty, okay? So you measure the uncertainty of the current, like in this case, and then say extended uncertainty is with coverage factor equal to 2 will be twice this value. Why? Because then it's more, we have more confidence if you take a range which is twice as large, okay? Okay, say uncertainty 1 milliamp, coverage factor 2, so 2 milliamps. Which in my opinion doesn't make just sense. Just give the uncertainty as you calculate it, and then if your customer wants coverage factor equal to 3, I hope he will not stupid not to be able to multiply times 3. It takes 1 milliamp and multiply times 3, and he gets 3 milliamps of uncertainty. If he wants very, very strong, 1,000 coverage factor, and he multiply 10,000. But just give the uncertainty, and then if he wants to be more confident, we'll just multiply times his own coverage factor, and he will get whatever the value he wants, okay? Okay.